All right, so we've started the recording. So this is the test review for the statistics, the full semester, the 16-week semester, test number 4, which covers chapter 6. My contact information is here. I'm Maxine Horn, the ASC. You can either email me here. Let me admit this person. All right. Or you can email me. I've put my other email in the chat. Either one of those will work. I know it's confusing. My first name is Brandy, but I go by my middle name of Maxine. But before we get started today, what I've done is I created a kind of like a handout that has what I feel is kind of the important information for this chapter. And what we're going to do is I'm just going to go through this handout. It's just 3 pages real quick, and we're going to refer back to it as we do the problems in this review session. And afterwards, I will include it as an attachment in the email that I send you guys that has the link to the recording. The reason that I don't want to send it just yet is because every time I look back at this handout, I find something else that I want to tweak about it. Either, maybe I misspelled something, or I think something should be placed somewhere different or something like that. So if we find things that we want to change about this handout as we're using it, I will change it and then I will include it as a link, as an attachment in the email to you. Okay, so it's a 3-page handout and it's on confidence intervals, right? That's what we're doing this chapter. So the first thing that I wanted to have was just like a visual representation of how we're dealing with the standard normal curve with confidence intervals. So when we talk about a confidence level of, and I used 95% as an example, but this is the same process no matter what percentage you have. That what that means is that you have an area in the center. It's this area here. The area in between these lines is 95% or 0.95, because remember the area under the curve is 1. So the area in between these two lines is 0.95 or 95%. So the remaining area in your 2 tails, those 2 areas added together is all total alpha. Okay, so that's the remaining area. Your remaining area is alpha, so 1 minus that. So if I have a 95% confidence level, this tail plus this tail is the other 5%, right? 95% and 5% is 100%. But when we're doing calculations, we're going to be looking at the just half, right? So like here and the z-score that corresponds to those. So we need to know what the area in just one of those tails is. Here, I think the light is on here. There we go. Now the light's on. That might be a little easier to see. So we want to know what alpha halves is. So if our alpha is 5%, alpha halves is half of 5% or 2.5%, right? So area in each tails is alpha halves. Okay, so that's the visual representation of what we talk about when we're talking about alpha and alpha halves. Another thing is that the z-score over here is going to be just the positive version of whatever the z-score over here is, right? I don't know if you guys remember that from, I think it was back in chapter 2 or something, where, if this is negative, I don't know, -2, then this is going to be +2 if the area in the tails is the same, okay? All right, so another thing on the handout is finding the sample size. So we've got 2 different situations. Either we're talking about means, right? Population, or I'm sorry, we're either talking about either having a population standard deviation, or we can estimate it if we have a sample standard deviation, or we're talking about proportions, okay? So while there are going to be a lot of things that you can do in the calculator in this chapter, and we'll go through how to do it in the calculator and how to do it by hand, you are going to need to know these formulas. Each individual instructor sets their class up a little bit differently, so you guys might be required to have these formulas memorized, or you might be given these formulas, but you're going to need to be aware of them, and you're going to need to be able to use them, even if you don't have to have them memorized. Like if your professor says they'll give them to you, you still need to know how to use them. So when you know your population standard deviation, your sample size is, you have to find your z-score or your z alpha halves or the z-score that corresponds to the particular confidence level, multiply it by the population standard deviation, divide by your margin of error, take that whole thing and square it, and that is your sample size. If you don't know your population standard deviation, then you can estimate it. You can use your sample standard deviation, but only if there was like a preliminary sample that was taken and its sample size was greater than 30. When we're talking about proportions, you either know p hat or you don't know p hat. If you know p hat, then you're going to do p hat times q hat. Don't forget that q hat is equal to 1 minus p hat. I'm not going to tweak the handout to write that because I have that written elsewhere on here. But anyway, then you're going to use your z alpha halves. You may also see like z sub c, like the z that corresponds to your confidence level. That's the same thing as the z alpha halves. Divided by your margin of error squared, that gives you your sample size. If you don't know p hat, then you have to assume that it's 0.5. So if p hat is 0.5, q hat's also going to be 0.5. So you put a 0.5 and a 0.5 for these. A little note about sample sizes is that we're talking about people. I can't have 0.02 of a person. So if my sample size says that I need 42.02 people, I can't use like quote unquote normal rounding rules and say, oh, well, that should go down to 42, because then I haven't met the threshold. I need to have at minimum 42.02 people. So I would have to take this and I would have to say, oh, that means I need 43 people. Okay, so we're always, I don't like to use the word round, but I'm going to use it here, round up. You know what? No, I'm not going to use the word round. I'm going to say we need to go up to the next whole number because we're talking about human beings here. All right, so that's the first page of the handout. So the second page of the handout kind of breaks everything down based on the 3 different types of situations that you're going to have. Okay, so when you're creating a confidence interval, you're either going to know your population standard deviation, or you're not going to know your population standard deviation, or you're going to be dealing with proportions, not means. Okay, so also note here, p hat is your x over your n. So, you know, if they have a study that shows that, you know, 72 people out of the 150 people that were surveyed said yes to something, that's going to be your p hat, is the x over the n. So I've got the reminders about what the symbols mean, right? You guys still need to know these symbols. The x with the bar, that's your sample mean. The n is your sample size. Sigma is your population standard deviation. S is your sample standard deviation. We talked about p hat. Q hat is the complement of p hat, and Q hat is calculated by 1 minus p hat. Okay, the big thing with these that people struggle with a lot is when am I using a z-score versus when am I using a t-score? So for these 2 situations, you use z's. The only time you use t is when you are using a sample standard deviation because you don't know your population standard deviation. That's the only time you use a t-score. Okay, then we have our error formula. So again, your instructor might want you to know these formulas. Your instructor like might want you to memorize it or might want you to just be able to manipulate it. But somehow you'll probably have to be using these. Okay, so again, we have our z alpha halves or z sub c times population standard deviation over the square root of n. Over here, it's the t-score rather than the z-score. And instead of population standard deviation, we have sample standard deviation. And then for the proportions, we have our z-score times the square root of p hat times q hat over n. Okay, writing your confidence intervals. This is just reminding you that, you know, there's different ways that it can be displayed, but here we're saying that our population parameter falls in between two values, and you would have to subtract these to get a number, add these to get a number. Same thing here. Our population parameter of mean falls somewhere in between here. Our population parameter of proportion falls somewhere in between here. Now down here, we have the requirements for each of these. So there are going to be some times where you're going to be saying, oh, wait, no, I actually can't do anything because I don't actually meet whatever your particular requirement is. So to use this setup, you have to know your population standard deviation. You have to have a simple random sample, and you have to have one of these two things. You don't have to have both of them. It's okay if you just have one of them, but you have to have at least one of them. Either it needs to be normally distributed, or you need to have a sample size of 30 or more. Okay, similarly over here, for this one, you need to know your population standard deviation. For this one, it's when you don't know your population standard deviation, but the rest of it's the same. You need to have a simple random sample, and then you need to either be normally distributed or have a sample size greater than or equal to 30. Right, so as an example, if I only have a sample size of 18, that's okay as long as I'm normally distributed, right? Or I could be not normally distributed, but I have a sample size of 50. That's okay. As long as one of these is met, that's all right. And then for the proportions, so you need to have two, well, you don't know your population standard deviation. You need to have two independent outcomes, right? You need to have either, p hat or q hat, right? There's only two things happening here, only two independent outcomes. It needs to be binomial. And also, your sample size times your p hat needs to be greater than or equal to 5, and your sample size times your q hat needs to be greater than or equal to 5. Both of those have to be true. So here it's either this or this, but with these, both of these have to be true in order for you to be able to use this. Okay. And then the third page is, okay, well, how do I actually do this, right? How do I calculate this? So I've got this is how we do it by hand, and this is how we do it in the calculator. So if we're finding a confidence interval in the calculator, it's pretty simple. Here's our three different scenarios. I'm going to pull this back up here real quick. So we had three scenarios, right? We had when we know our population standard deviation. Sorry, yeah, I'm pointing to the wrong thing here. I was pointing at that, I was like, wait, did I write the wrong thing? When we know our population standard deviation, when we don't know our population standard deviation, and when we're dealing with proportions, right? So those are the three scenarios that we have here. And which menu you go to in the calculator depends on which of those scenarios you have. These are the tools that you use in the calculator if all you want to do is create your confidence interval and you want to just plug it into the calculator and just get your interval. Okay. If you have to do something like maybe, let me go back to this, maybe you are not being asked for a confidence interval, maybe you're being asked for determining a sample size, well, you need to know a z-score, right? You need to know a z-score, so you have to calculate a z-score. So you might be trying to specifically find a z-score. Again, you can do that in the calculator. Or you could do it by hand. So we're going to go through, I'm not going to go through in as much detail here because we're going to do these on the actual problems. But excuse me. But I will be providing you guys with this handout as an attachment when I email you. Okay, so I see somebody typing, so I'm going to hang on for just, oh, okay, gotcha. Yeah, no worries. You're welcome. So let's go ahead and dive in. And like I said, I'm going to show you a few ways because there's like the fully by hand way, there's the partially by hand way, and there's the all in the calculator way. So a grade point average collected from a random sample. Okay, so first of all, that's great. It's a random sample because that's a requirement, right? Of 150 students right off the bat, N is 150. I'm going to start labeling stuff, right? It produced, that should say produced, a mean of 2.86. So that sample produced that mean. So that's my sample mean. That's my X bar, 2.86. Assume that the population standard deviation, so that's this, is 0.78. Construct the confidence interval for the population mean, mu, if your confidence level is 0.98. So my confidence level is 98% or 0.98. Okay, so if we wanted to go back, just so that I can kind of show you how you would use this handout and say, so they want me to create a confidence interval. Sorry, wrong page here. I'm finding a confidence interval. Okay, I'm either going to do it by hand or I'm going to do it in the calculator. We're going to start by doing this by hand. Then we're going to do part of this by hand part. We're actually going to do in the calculator. And then we're going to do it again fully in the calculator. Okay, so the first thing that we need to do is we need to calculate our Z alpha halves or our T alpha halves. And the reason that we have to do that is because, pull this up a little bit here. Actually, real quick, let's go back to the question. I do have a population standard deviation. So I just want to point that out. So I know that I'm going to be in this column here because I know my population standard deviation. Okay, so when I know that, I'm going to be creating a confidence interval. This confidence interval is I have to add and subtract the error from my sample mean. So I need to calculate the error. Okay, here's the formula for my error. Okay, well, the things that I put in my error, I have these two, but I don't have this. So I have to find this, right? So we're kind of going backwards from this is what I need. So okay, I have to calculate that. Okay, in order to calculate that, this is what I need. Okay, I'm going to calculate this, right? So look at your kind of end step, like what are we working towards? And then go back and say, okay, how do I find each of these elements? So I'm going to need to find a Z alpha halves. We're going to do this by hand, then we're going to do that in the calculator. Then we're going to by hand calculate our error so that we can by hand calculate our confidence interval. Okay. All right. Because those are our steps, right? Calculate either your Z alpha halves or your T alpha halves. Then plug those values into your margin of error formula, and then add and subtract your margin of error from your sample statistic, which is our X bar, our sample mean, to create our confidence interval. Okay. All right. So I shouldn't have taken that away because calculate your Z alpha halves. Okay, well, how do I find my Z alpha halves? If your confidence level, which by the way, our confidence level is 98%, if it isn't shown in your critical values table that's in your book, then you're going to do these steps. So let's grab the book. And remember, even if you're taking the class online, you have access to the textbook. I know sometimes people don't like look at the textbook, but you can. Okay. So in your book on page A18, right, or I'm sorry, A16, not 18, page A16. So this is in the back of the book, page A16, we have this page, right, the standard normal distribution. But at the bottom, it has this little diagram that says critical values, level of confidence, and the Z sub C, right? So I mentioned earlier, you can see it as Z alpha halves, but you will also often see it as Z sub C for critical value. So if I have a confidence, and also you can see here that it's saying, hey, this is the area in the middle. So it gives some very common levels of confidence, 80%, 90%, 95, and 99%. Well, unfortunately for us, this particular problem, ours is not here. But if it were here, if it were one of these four, that would be great, right? Because then it's just giving us our Z-score. We don't have to go look in the table for it. It's just giving it to us. But this one, it didn't, so we have to actually calculate it. Okay, so, or I say calculate it, we have to find it. So it isn't shown in the table. So what we have to do is we have to first find what is alpha halves? What is the area in one tail, right? Remember, that's what alpha halves is, okay? So we're going to find alpha halves. So we have just kind of a visual of what's happening here, right? We have 98%, okay? So 1 minus 98% is going to give us 2%, right? So this tail plus this tail all total, that's our alpha, is 2%, but we want to cut that in half. We want just one tail, alpha halves, is 1%, right? Does that make sense? So alpha halves is 0.01. Okay, why do we need this? Because we need to know what the area is to the left of that. We need to know that that's 0.01 so that we can find the corresponding Z alpha halves. Okay, so we go to our table and we find in the body of the table, we find 0.01. So that's going to be, okay, so we have 0.0099 and 0.0102. This is 2 away, this is 1 away. You can kind of think of it like that, right? So this is closer. So we don't have the exact value, but this is closer. So this corresponds to negative 2.33, okay? So we have negative 2.33. Except when we're doing these problems, we always just take the positive, right? Because this z-score over here would be a positive 2.33. So when we go to use this in our calculations, we're just going to use positive 2.33. Okay, so we looked that area up in the body of the table, and we used the positive value, positive 2.33. Okay, we got our z alpha halves. Now we're going to plug that value and the other numbers that we need into our error, our margin of error formula. Okay, so what's our margin of error formula? Got so many papers. Our margin of error formula right here, z alpha halves times population standard deviation over the square root of n. Okay, so we're going to say margin of error equals z alpha halves times population standard deviation over the square root of n. So let's plug in everything that we have. We calculated our z alpha halves is 2.33. Our population standard deviation, we were told up here, is 0.78. And our n value, our sample size, is 150. Okay, so we're going to, oh, I forgot I was also going to show you how to do this in the calculator. I'll do that in a minute. Clear, clear, clear. Okay, so we're going to do 2.33 times 0.78 divided by the square root of 150. Okay, and we get this number. So I'm going to go to like 3 decimals here, and then we'll round our final answer to 2, because you can see in the in the answers that we have here that they've gone to 2. So we'll go to 2 decimals in our final answer, but for right now, I'm going to go to 3. All right, so we calculated our margin of error, right? That's our margin of error is 0.148. And why do we need our margin of error? Because we're going to take that and we're going to add it and subtract it. And you can write it this way or you can write it this way. I like writing it this way because it's like a full sentence here, from our sample statistic. Because remember, big picture, what we're doing here is, excuse me, is that you said you got that in the normal calculator. You mean like you got the same number as I did when you plugged it in? Yeah, just let me know what you meant by that, but I'll keep going while you type. That what we're doing here is we're saying that we can be a certain level of confident that the true population parameter exists between 2 values. And the way that we, okay, gotcha. Thanks, Mohammed. And the way that we say what those 2 values are is we take our sample statistic and add and subtract whatever our margin of error is. Okay, so looking at this, it might be a little, I don't know, confusing, but if you think about it in terms of like if somebody just said to you like, you know, oh, I think I got a 90 on that test, plus or minus 5%, Well, you know what that means. That means that either they got a 90 plus 5 or they got a 90 minus 5, right? They got somewhere between an 85 and a 95, right? Another way you could see it as like, oh, I got a 90 or I got 5 more or I got 5 less, right? I'm somewhere in between those two values, right? This is like pretty numbers. We're dealing with maybe not so pretty numbers, but it's that same idea of plus or minus some margin of error. Okay, this is our margin of error. So we're going to do our sample statistic minus our margin of error is less than our population parameter, which is less than our sample statistic plus our margin of error. So our sample statistic, our X bar, our sample mean, was 2.86. And from that, we're going to subtract 0.148. And then 2.86 plus 0.148. Okay. So, and if I round that to 2 decimals, I'm getting 2.71. And then this is cool. I just learned this the other day. I'm like, oh, wow, that's great. If you arrow up and you highlight the thing that you just typed and then you hit enter, it's like it copies and pastes it. And then you can arrow back and you can change the minus to a plus. That might save you some typing depending on what you've typed in. Sometimes it's not going to save you typing, but sometimes it can. All right, so if I round that to 2 decimal places, the 8 turns, so the 8 turns that 0 into a 1, and we have 3.01. Okay, so the population mean is somewhere between 2.71 and 3.01. I'm sorry, more specifically, we can say with 98% confidence that the population mean is between 2.71 and 3.01. Right? That's the whole idea of confidence intervals of what we're doing here. It's this interval at this level of confidence. Okay, now this was the fully by hand version. Okay. If we go back up here to when we were calculating our z-score, you can still do the rest of it, the rest of it by hand, but you can do your z-score in the calculator. So let's go back to how to do that. If I want to find my z alpha halves in the calculator, I still have to kind of start the same way. Well, actually, not necessarily. Okay, we have a 98% confidence interval or confidence level, right? What we're going to do is we're going to go to second vars, which is the distribution, right? So second vars, and we're going to go down to inverse norm, number 3, inverse norm. So inverse norm is what you use when you have an area and you want to find either a z-score or an x value. We're going to be using z-scores in this chapter. We're not going to be using it to find x values. So because we're going to be using z-scores, we need to leave our mean and our standard deviation as 1. If you put in things other than 0 and 1 here, then you're not going to get a z-score. You're going to get an x value. We don't want an x value, we want a z-score. Okay, so what do we put for the area? Well, there's a few ways that you can do this, okay? So you can either put in your confidence level, which our confidence level is 0.98, and say, yep, that's in the center, right? Because my confidence is, right, we're drawing a picture of what's happening here. My area is 0.98 in the center, right? And then hit enter. And it's going to say, oh, you want an area of 98 in the center? And we say yes. And it gives us the negative z-score that defines that area and the positive z-score that defines that area, right? Negative 2.33 and positive 2.33 if I were to go to 2 decimals here. Remember, the table only went to 2 decimals, so that's all we could do there. If you wanted to, you could go to 3 decimals here. So that's one way you could do it. Or if you were feeling like you wanted to do a little bit extra work, you could, or maybe you already calculated and said, oh, well, I know the area in the left tail is 0.01, and you don't want that extra work to go to waste, then when you go back, when you go second vars and hit number 3 to do inverse norm, you can say, well, I want to tell it an area of 1%, and then I'm going to tell it that that's the area in the left or to the left of the z-score that I'm asking it about, right? And then if we paste that, we're getting the negative z-score. So what do you think is going to happen if we do this again, but we tell it that, oh, this is the area to the right of the value, the z-score that I want you to find? We're getting the positive, right? So if you tell it that the area in the center is 98, it's going to give you the two z-scores, positive and negative, that define that area. If you tell it that 1% is the area to the left, it's going to give you the negative z-score. And if you tell it that 1% is the area to the right, it's going to give you the positive z-score. Okay, so these are the three different ways that you can do that if you wanted to do that part in the calculator. So to kind of, I'm going to actually write that out here. I'm going to say, or you could do, so second vars, the str, and then it's 3, which is inverse norm. And then you either do, yeah, 0.98 in the center, or you do the area in one tail, which is 0.01, and you tell it either left or right. I don't know why I wrote that down so far. But as long as you know that whatever z-score you get, you have to use the positive one of it, right? Because for our margin of error, we don't ever want a negative number. We always need to make sure that this is positive. So we can't use a negative z-score here, right? This has to be a positive z-score so that we get a positive margin of error. So we're going to subtract and add it. Okay. All right, so we did it fully by hand, and then I showed you how to do partially in the calculator. Like you can find the z-score in the calculator, and then once you find the z-score, you plug it into your error formula, and then plug that in to get your full confidence interval. Another option is to do it 100% in the calculator, right? When the population standard deviation is known, to find your confidence interval in the calculator, we're going to go to tests, and we're going to do an interval, z interval. Okay. So this is how to do it fully in the calculator. So you go stat, you arrow over to tests. You can either arrow left or arrow right twice. And then you're going to go all the way down to number 7, or you're just going to hit number 7 where it says z interval. Quick note, the reason that it's z, the other handout here. In this situation, we use z interval. In this situation, we use, well, actually we use one prop. Well, we use one prop z int, but it's a z. In this one, we use a t interval. So I mean that's on the other thing, but just the reason it's z or t is because we're using either a z-score or a t-score. Okay. Okay. So z interval. If you have highlighted data, make sure that you change it to stats. Okay. In this class, you guys are not going to be using the data part here. You're only going to be doing it with the stats. So make sure stats is highlighted. And then you're just going to plug in everything that you have, right? So in the calculator, this is stat, tests, 7, which is z interval. And then we just plug in what we were given, right? So it's asking us for this, 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 and this. Okay, what's our population standard deviation? Well, they told us that it's 0.78. What's our sample mean, or x bar? They told us that it's 2.86. What's our n? What's our sample size? That was 150. And then what's our confidence level? They want us to be 98% confident. So we're going to plug all that in. 0.78, 2.86, 150, and I happen to already have 0.98 there, but if I didn't, I would change it, and then you hit calculate, and there it is. That's it. That's our confidence interval. That's all the work that we had to do. And if we wanted to write it out the way that I wrote this here, I always prefer writing it that way because, like I said, it's like a full sentence. It's reminding us, hey, my population parameter, my population mean, I can say with 98% confidence that it's in between these two values, right? So my population mean, I can say with 98% confidence that it's in between these two values. So I have 2.7118. If I round that to 2 decimals, that's 2.71. 3.0082, if I round that to 2 decimals, that's 3.01. And wouldn't you know it, that's exactly the thing we got here. So while it is important for you to know what goes into this, it's also really helpful to know how to just go to the calculator and plug this in, okay? So, oh, sorry, I see somebody wrote something. I got a notification. I got to close here. Do you round up with the z-score as well? How will I know how many decimals? So what I like to do is I like to go out one more decimal beyond what my final answer is going to be and wait to round to that number of decimals until the end of the problem. Because if I round kind of every step of the way, that rounding can really like compound and, and add up and potentially make a difference. They don't necessarily try and trick you. Like if you look at this answer, it's not like there's a 2.70 that's an answer, right? They're not trying to trick you with the rounding. So it shouldn't cause any issues, but I just like to always be extra careful and go one decimal more than what I need until I get to the very last step. And only at the very last step round to how many ever they told me to, or how many ever the answer is. So that's what I do with the rounding. Excuse me. But if you're doing it this way, where you're doing it fully in the calculator, you don't even have to worry about that because you just take the number that it gives you in the calculator and you just round to whatever they have. Okay. All right. So that was the 3 different ways to do that one problem. So now let's do it again. Okay. All right. In a sample of 10 randomly selected women, N is 10, it was found that their mean height, so the sample mean, 63.4 inches. From previous studies, it can be assumed the population standard deviation is 2.4, and that the population of height measurements is normally distributed. Construct the 95% confidence interval for the population mean. So our confidence level needs to be 0.95. So a couple things to note here. You might have seen that n equals 10 and thought, oh, wait a minute, I can't have n equals 10. I'm supposed to have n is greater than or equal to 30. Well, that's okay as long as it's normally distributed. And thankfully, they clarified for us, hey, don't worry that your n is 10 because it's normally distributed. Okay, so we all the boxes here, so we can use we can do this process. I'm going to do it in the calculator first, and then we're going to do it by hand. Okay, so in the calculator, if I know my population standard deviation, I'm going to do the z-interval. So I'm going to do stat tests z-interval. I'm going to make sure I'm on stats and not data, and I'm going to plug in all the values that I have. Okay. So we go stat tests. What was that, number 7, which is a z-interval. And I'm going to plug in the values. So what values are they looking for? All right, our population standard deviation, which is sigma, is 0.24. Our sample mean, which is X bar, is 63.4. Our N, which is our sample size, is 10, and our confidence level, C level or CL, is 0.95. Okay, so let's plug and chug. Well, really, the calculator is doing the chugging. And there we go. Again, if I wanted to write it nice and pretty, I mean, it's just saying, hey, here's the lower end, here's the higher end. But again, I always like to write it like this: 61.91, 64.89. If I'm going to, oh, I'm sorry, it only went to 1 decimal, not 2. So let me erase that, and then this would round up to 0.9. That's a terrible eraser. Let me get my other eraser. I usually have my eraser out and ready. Sorry. Okay, well, hopefully you can see that well enough. Okay, so that's if you're doing it fully in the calculator. Imagine how many problems you could get through that quickly if you could do all of them like that in the calculator, right? So keep that in mind when it comes to the test. You don't have to, unless they say specifically that you have to do it by hand, you don't have to do it by hand, right? Just do it in the calculator. I mean, there are going to be problems where they might ask you to just do part of a problem, and that's their way of saying, hey, I need you to prove to me that you can just do part of this and do it by hand. But otherwise, save yourself the work, save yourself the headache, learn how to use the tools and the technology that we have available to us. Okay, so now let's do it by hand. Okay, so again, if we go back to our, hey, how do I do this? I'm going to calculate my Z alpha halves. I'm going to plug that and the other values that I need into my margin of error formula to get my margin of error. And then I'm going to add and subtract my margin of error from my sample mean to get my actual interval. Okay. All right, so how do I calculate my Z alpha halves? If my confidence level is on the table, great. Well, what was our confidence level? 95%. What does the table show? Does my table have 95%? Woohoo! My table's got 95%. Awesome. 1.96. Now, let's say that you forget to look down here and you go to look it up in the table. Let's pretend that we're going to do that, okay? So we know that we should get 1.96, but let's pretend that we don't know that. We need to, in order to find Z alpha halves, we need to find alpha halves, okay? So remember that's 1 minus your confidence level divided by 2, because remember what's happening here, right? If you need to draw, I'm a very visual learner, so I always like picture what's going on, right? So 95 is the area in the middle. Alpha is the area of the two tails added together. So that's going to be 5%. So alpha halves is the area in just one of those halves. So that's, let me kind of catch up on I'm up here. So that's going to be 2.5%, right? 2.5 is half of 5. So 0.025. The area in one of these tails is 0.025. So my Z alpha halves is going to be the Z-score that separates the bottom 2.5% from the rest. So I'm going to look up in the table 2.5%, okay, or 0.025. And there it is right there, 0.025. So I say, all right, that's a negative 1.96, except I'm not going to take the negative, I'm going to take the positive of that. So 1 point, or again, we remember that down here, if I have a confidence level of 95%, my corresponding Z-score is 1.96. Okay. All right. So either way, I get that my Z alpha halves is, I mean, that one is negative 1.96, but what we're going to use in our formula is 1.96. Okay. And what's our formula? Our formula, Z alpha halves times population standard deviation over square root of n. Once we find this, once we get our margin of error, we're going to add and subtract it from our mean, right? Add and subtract it from your sample mean. Okay. Also, real quick, if I wanted to find my Z alpha halves in the calculator, right? So what we just did, if we wanted to do that part in the calculator, we're going to do second vars inverse norm. Second vars inverse norm. I can put in my confidence level and tell it, whoops, that it's the center, right? And then I get my negative and positive z-score that correspond to the z-scores that separate the middle 95% from the two sides. Or I could say, well, the area in one tail is 0.025. So I'm going to say 0.025, and that's either in the left, and I get the negative z-score, or it's in the right, and I get the positive z-score, right? Hopefully you guys are seeing the relationship here between these three different ways of finding this in the calculator so that you can feel confident doing it whichever way you feel like doing. They're all going to get you the number that you're looking for, which is a positive 1.96 when you go to two decimals, which I'm going to because I looked it up in the table and the table only gave me two decimals, which is fine. If I were only doing this, or not only doing this in the calculator, but if I did calculate this in the calculator, I would say, hey, yeah, sure, I'll go to three decimals. Excuse me. But that would end up like, well, anyway, that would end up being the same thing because it's all 999. But anyway, just be comfortable finding your z-score and be comfortable doing the whole thing in the calculator. Let me write out real quick. Or second vars. Inverse norm. And then you can do 0.95 in the center. I'm not going to write this out every time just because we're going to do this for every single one of these. Or you can do 0.025 on the left or the right. The more you do it, the more comfortable you're going to get with it. So do it a bunch of times. Okay, so the margin of error, again, our formula is Z alpha halves, or Z sub C, times population standard deviation over square root of n. So I'm going to plug in 1.96 times my population standard deviation was 2.4. My n was 10. And I'm going to take that and I'm going to go to three decimal places. Okay, so I get 488, 1.488 when I go to three decimals. Okay, so now that I have my margin of error, I am going to construct my confidence interval. Right, so my confidence interval says that I have my sample mean minus my margin of error is to the left of my population mean, which is to the left of my sample mean plus my margin of error. So what was my sample mean? 63.4 minus 1.488. 63.4 plus 1.488. Okay, so if I take that to one decimal place, I have 61.9. Yep, yeah, Mohammed, so that, oh, wait a minute, you got 14 instead of 1.4. So I would plug that in again because you should have 1.4. Okay, yeah, as long as you got 1.4 and not 14, then yes. So it looks like your calculator goes out to more decimals than mine does. That's fine, but you're not going to need that many for what you guys are doing in this class. And then again, that little thing where I can arrow up, highlight it, hit enter, then go back and change it. I don't know that that saves me any clicking, but I don't know, it's kind of fun. And again, if I go to 1 decimal here, that's going to be 64.9. So I can either do it this way, even if I save myself some time on this first step and find the z-score just in the calculator, I'm still plugging it in here, and then I'm still adding and subtracting it here, or have the calculator do it for me, right? So it's important to know that this is how you do it, right? It's always important to know where the formulas come from, that there are formulas, be comfortable manipulating the formulas and using them, but also, like with many things, you also part of the class is teaching you how to use the technology and the tools that you have. So they do expect you to be able to also do this in the calculator. So keep that in mind in terms of like, hey, I only have this many hours to do this test, right? Like it's a timed test. That's because they're not expecting you to take the time to do every single one of these by hand. They're expecting you that you're doing it in the calculator when they calculate the amount of time that they're going to give you for it. Okay, number 3. So a nurse at a local hospital is interested in estimating the birth weight of infants. How large a sample must she select? Right, so we're going to be doing sample sizes here. How large a sample size must she select if she desires to be 99% confident, so our confidence level is 0.99, that the true mean, right, the population mean, is within 2 ounces. That's my error. My margin of error is 2. I want to be within 2 ounces of the sample mean. The population standard deviation of the birth weights is known to be 7 ounces. Okay, so label what you're given and then go and see what you should be using. We are doing, I'm going to kind of fold this a little bit here. We are finding a sample size, right? We were given our population standard deviation. We're going to use this formula, okay? We need to find our Z alpha halves. The Z alpha halves is based on your confidence level. So we're going to find our Z alpha halves, and then we're going to plug that in here, okay? So to find our Z alpha halves, let's do it in the calculator. We could do it, right? Remember, we could do that by hand where we draw it and we say 99% is in the middle, and we say 1% is in either tail, or I'm sorry, 1% is in both tails together, so 0.005 is in each individual tail, and we go look that up in the table. Or maybe we just look at the table and check to see, hey, 0.99, oh, sorry, you guys can't see that, 0.99 corresponding z-score is 2.575, right? So you can do that, or you can do it in the calculator. Now, in this case, it's actually faster to look it up in the table if the table has it. 2.575, great. But just for illustrative purposes, if we were going to do it in the calculator, second vars, inverse norm, the area in the middle is 0.99, and this is the area in the center, right? If I don't want to have to do any extra calculations, I'm just putting my confidence level in the center, and it's going to tell me my positive and my negative z-scores, right? Now, you might look at this and say, hey, wait a minute, if I went to 3 decimals, I would actually be rounding to a slightly different number. Well, that's okay. We kind of talked about this a little bit before where, you know, your final answer is, they're not going to screw you on the rounding. Sorry, I don't know if I'm allowed to use that language, sorry. But they're not going to try and trip you up with the rounding. And keep in mind, you know, these numbers, they're not exact numbers, right? We go to a few decimals, but we don't go to a million decimals. These are approximations. So I'm going to use what the table has, which is 2.575. And then we're going to take that and we're going to plug it into our formula, which is Z alpha halves times population standard deviation over the margin of error, and that whole thing is being squared, okay? So just be careful of your parentheses when you're doing this, right? 2.575 times, oh, sorry, I should write it out by hand first. 2.575. What was our population standard deviation? It was 7. It's times. What's our margin of error? It's 2. Okay, so 2.575 times 7. You know what, I should have, let me do that again, because I'm going to put my numerator in parentheses, and I want the whole fraction in parentheses. Okay, so you see how I plug that in there? I have the whole thing in parentheses, and then I have separately, I have my numerator in parentheses. Right, you don't have to have that because order of operations says to do this multiplication before you do the division. But for those of you that are not super comfortable with order of operations and plugging things into the calculator, just use extra parentheses just to be sure. Okay, now when I do that, I'm getting this number. This gives me in the calculator 81 point, and this is actually technically approximatate, 0.22515625. And if you were going quickly through this, and you did this, and you looked at these answers, you might be tempted to choose 81. But you're not going to, because you're going to pause and you're going to remember the context of this problem. And you're going to say, I'm not just blindly plugging numbers into a calculator and spitting them back out. I am thinking critically about what is being asked of me. What is being asked of me is to find how many people I need in this sample. I'm looking for a sample size. So this is people. So we're not using normal rounding rules because this is the threshold of how many people I need to have in my sample in order to actually be 99% confident that I only have a margin of error of 2. So if I need 81.22 blah, blah, blah people, and I only do 80 people, if I only include 80 people, I'm sorry, 81 in my survey when I needed a little bit more than 81, then I'm not going to be that confident, or my margin of error is not going to be that small. This will be incorrect. So what you have to do is you have to take your number, whatever your number is, and go up to the next whole number. Right? So always remember that with your sample sizes, with your n's. Whatever this is, if you have any decimal over here at all, even if it's 0.000001, you need to go up to the next whole number. And it's very rare that you're going to get just a flat number like 0, like 0.0. I have yet to see a problem where the math works out that way. You're going to get a decimal, you have to go up to the next whole number. So that's why the answer is 82 and not 81. Okay? All right. Okay, which statistic, sorry, hold on, let me get my, got all these handouts all around here. Okay, which statistic is the best unbiased estimate for mu? Remember, mu is our population mean, right? X bar is our sample mean. Lowercase sigma is our population standard deviation. S, it's just S, is our sample standard deviation. P is just P is our population proportion. P hat is our sample proportion, right? So the best unbiased estimate for your sorry, you guys can't read that. The best unbiased estimate for your population parameter is the corresponding sample statistic, right? So the best unbiased estimate from you is X bar. Okay. All right. construct the confidence interval for the population mean, mu, and they've just gone ahead and just given us all the numbers, right? They're just throwing the numbers out there. So they're not giving you any context. They're not giving you a word problem. They're just saying, hey, here's the numbers. Show me that you know what to do with these, okay? So we have been given a population standard deviation. So again, let's just do this on the calculator, right? We're going to go stat tests. We're going to go down to number 7. This is a Z interval, and we're going to plug in the numbers that it gave us. It gave us a population standard deviation of 0.5, a sample mean of 5.3, an N of 58, and a confidence level of 0.98. And there it is. That's my answer. See how much time that took? I didn't even write anything down, right? I didn't have to label, I didn't have to put numbers next to the symbols because it already did it for me. And it took me all of, what did that take, 15 seconds to do that problem, right? Whereas, I mean, I know I was taking a little bit longer when I was doing it by hand because I was explaining it, but even if I hadn't been explaining it, it takes several minutes to do that. Versus here, plug it into the calculator, get your answer, okay? Just make sure that you're always going to how many ever decimals it tells you to, okay? All right. Okay, you're given the sample mean and the population standard deviation. Use this information to construct the both 90 and 95% intervals for the population mean. I'm going to adjust my headphones a little bit here. Hold on. Okay, they're starting to hurt my ears. So I'll still be able to hear you guys. Okay, if there's a noise or something. So we're going to do both of these, and then we're going to interpret the results and compare the width of the intervals, okay? So it's giving us all this information, so we do have to go ahead and label this. All right, from a random sample of 40 business days, N is 40. The mean of that sample, the mean closing price of a certain stock, X bar, was 117.61. Assume the population standard deviation is 1023. We're going to construct a 90%, and then after we do that, we're going to construct a 95%, okay? So again, we're just going to do this in the calculator, right? So we're going to go stat, tests, number 7, Z interval. We have 10.23, 117.61, 40, and for this first one, we're going to do a 90% confidence interval. Okay, so we get just what we got here, 114.95, 120.27. Okay, now we're going to do the same thing, but a 95% confidence interval. Stat test number 7, and we're going to keep everything the same, but we're going to increase our confidence, okay? Before, we only needed to be 90% confident, but now we need to be more confident. Okay, and we get these numbers. So now they want us to look at these two different intervals and compare them. Which one is wider? So if you're having trouble looking at these numbers and determining that, kind of draw a picture in your head of, that needs to be lower, of what's happening. So we have our sample mean is 117.61. Okay. Actually, you know what? I'm not even going to worry about writing my sample mean. I have, for this first one, I'm going 114.95 to 120.27, right? That's, I'm going from here to here. I can be 90% confident that my true population parameter is between these two numbers, that it exists somewhere in there. But if I want to be 95% confident, these are the numbers that contain my interval. Okay, 114.44, that is a lower number than this. It's somewhere to the left. Maybe not very far to the left, but it's to the left. 120.78, that's more than this. Not a ton more than it, but it's more than it. So if I need to be 90% confident, I'm going from here to here. But if I want to be more confident, I have to expand the set of numbers I'm looking at, right? 95% confident is here, but if I only care about being 90% confident, I can narrow my view. The way that I think of it is like, you guys have probably heard the phrase like widening your net, right? If you want to be extra sure that you include something, you got to widen your net. You know, if you lose your keys and you're not too worried about it, maybe you just look in the living room, right? But if you lose your keys and you're like, no, I need to leave right now, I need to go look everywhere. I need to expand where I'm looking. Can we still get this answer by subtracting the larger number from the smaller number? Um, can you clarify backwards? Okay, the smaller number from the larger number. Um, do you mean like saying like do 114.95 minus 114.44? And then like, yeah, if you do this minus this, that's just going to tell you what the difference is between them. And you're not necessarily worried about knowing exactly what the difference is between them here. You're just more worried about saying that this number is farther to the left on the number line, right? So like this is the number line where we have, you know, I don't know, maybe zeros here, and then we have like 1 and 2 and 3. And if I told you to plot 1.7 as compared to 1.4, 1.7 is going to be, I don't know, somewhere about there. But 1.4, I really just need to know where it is in relation to 1.7. This is a smaller number than this, so it's going to be to the left because it's smaller, right? So 114.44 compared to 114.95, if you're ever confused about like, wait a minute, what, which one's whatever, think about money, right? I always think about money. Would I rather have $114.95 or $114.44? Well, that's more money, so I want that one. That's bigger. It's to the right on the number line. Okay, so like 120.27 minus 114.95, then compare. Oh, yeah, I see what you mean. Yeah, so you're saying like, well, how wide is my net? Yes, you can absolutely do that too. So you can say, well, this goes, so let's do that. So I can say 120.27 minus 114.95. So from here to here is a total of 5.32. Whereas if I do 120.78 minus 114.44, that total is my net has gone wider. It's 6.34 all the way from here to here, whereas this is only 5.32 from there to there. So yeah, good question. You can absolutely do it that way. If depending on what you're looking at, you don't necessarily have to do that. I was doing it like this for like visual illustrative purposes, but if you can just look at these numbers and say, well, which of these is like farther to the left on the number line, which one has gone farther, that's going to be the wider net, right? So this one is farther to the left, it's lower, it's the wider net. So which is wider? The one that went farther to the left, so the 95% confidence interval. And then they want you to interpret it. So, I mean, really, they're just restating what we've already talked about, that we can be 90% confident that the true population mean falls between 114.95 and 120.27, and we can be 95% confident that the population mean falls between 114.44 and 120.78. Okay. All right. Okay, so then we have another question that's almost exactly the same. So blah, blah, we're going to be doing 90 and 95 again. They could give you different percentages, right? Okay, so let's go through and label things. From a random sample of 36 months, okay, so my N is 36. From this date through this date, the dates don't matter. Well, not that they don't matter, but in terms of like assigning a like a symbol to that. there's not a symbol that's assigned to the dates. They're just specifying which 36 months. The mean number of tornadoes per month in the United States was about 97. Assume the population standard deviation is 112. So they did give us the population standard deviation of 112. So we are going to be able to use that same menu we've been using of Z interval. So we go stat tests, Z interval, and we give it all of the information that we have here. We have population standard deviation of 112, a sample mean of 97, a sample size of 36, and we're going to first do a confidence level of 0.9. And there we have it. Again, if we round to 2 decimal places, these are the numbers that we're going to get. So if we do the exact same thing with now 95%, so again, stat, test, number 7, Z interval, and the only thing we're changing is that we're changing this to 0.95, we get our new numbers. Okay, so excuse me. If we look at compare these two numbers, or we can compare these two numbers, which of them goes farther out on the number line? So this number is less than this number. It goes farther to the left. Oh, you can't see my hand. I'm doing like farther to the left. This number is bigger than that number. It goes farther to the right, which means this is creating a wider interval. The 95% confidence interval is wider. Right? They're trying to get you to see a pattern here, that if all other things are equal, the more confident you become, the wider your net has to be. Right? So, and then again, it's saying if I'm 90% confident, I mean, we could do the numbers here if we wanted to. Yeah, 66.30 to 127.70 versus 60, and this is not to scale, but to 133.59. So from here to here, we're only 90% confident. But if we want to be 95% confident, we have to widen our net to that. Right? So we can be 90% confident that the population mean number of tornadoes is between these two bounds. But if we want to be 95% confident, it's between these two bounds. Okay. All right, so this question is taking what they were trying to show you in the last two questions and putting it into words, okay? So if all other quantities remain the same, how does the indicated change affect the width of a confidence interval? So if the confidence level, an increase in the level of confidence will what the confidence interval? It's going to widen, will widen, which is what we were just talking about. Right, if I want to be more confident, then I have to widen my net to be extra sure that I actually catch the value that is in there somewhere. So what about if I increase my sample size? So the more people I have, the more likely I am to be able to get closer to the true population mean. So if you think back to, I think it was chapter 3, where you guys were learning about probabilities with like flipping coins and you know, rolling dice and things like that. One of the things you guys learned was that the more you do it, the closer it gets to the theoretical probability, right? If I flip a coin 2 times, I'm not necessarily going to get 50% heads and 50% tails. But if I flip a coin 10 times, it's maybe going to be about 50-50, but I could still very well have like 7 and 3 rather than 5 and 5. But if I flip a coin 1,000 times or 10,000 times or 50,000 times, I will slowly but surely approach exactly 50-50. Okay, so that's kind of what's happening here. The bigger my sample size, the more likely I am to contain the actual population parameter. Because if you think about it, you're getting closer to the whole population, right? You have a population parameter, and the bigger your sample size gets, the closer your sample is getting to your actual population, right? Like if we talk about maybe like the population of all Daytona State College students, and I decide to take a sample of students at the Palm Coast campus. Well, that's just a small sample. But if I then say, okay, I'm going to take students at all the students at Palm Coast and the ones at New Smyrna. Well, I've just increased my sample size. I'm going to be I'm going to be narrowing the interval of numbers because I'm getting closer to my population. And then if I say, well, I'm going to look at all campuses except for Deltona, then I'm really, really close to the whole population. So I'm really going to be able to super narrow my interval, right? And when I talk about narrowing my interval, I'm saying like instead of the interval being from here to here, I narrowed it. I don't have such a wide interval anymore. And that interval is going to get smaller and smaller until it's pretty small if I am increasing my sample size. So, okay, what actual word are they looking for? Yeah, it's going to narrow. Not marrow, not bone marrow, narrow. It will narrow the confidence interval, okay? And then an increase in the population standard deviation. Okay, so we got to go back and we have to remember, okay, well, what is population standard deviation? It's how the population is deviating from the mean. Is there a lot of deviation from the mean? Is there a little deviation from the mean? If we have a lot of deviation from the mean, then we're going to have a wider interval because there is a wider deviation. Just trying to think of a better way to say that, but it's going to widen, it's going to widen the confidence interval. Okay. All right. Construct a 95% confidence interval. Okay, let's start labeling things. Confidence level 0.95 for the population mean. Assume the population has a normal distribution. That's good. A random sample of 16 fluorescent light bulbs. That's my N. Also, thank you for letting me know that it's a random sample, right? A simple random sample. 16 fluorescent light bulbs has a mean life, right? The sample mean of 645 hours with a standard deviation of 31 hours. That standard deviation is a sample standard deviation, right? That's the standard deviation of this sample, not the standard deviation of the population, right? So that means that we are doing this one, right? Because our population standard deviation is unknown. So don't forget, excuse me, that means we're going to be using a t-score, not a z-score. Our margin of error formula is very similar, except we're using a t-score instead of a z-score, and we're using our sample standard deviation instead of our population standard deviation. Okay. It does meet this criteria. It's a simple random sample. It is normally distributed. Our N was only 16, but that's okay because I need either one of those to work or to be true, and this one is true. So it's okay that this isn't because this is. All right, so just like we did with the ones that we did that were in this column, in this one, I'm going to do this fully by hand, and then I'm going to show you how to do it in the calculator. Okay. Well, fully by hand, partially in the calculator, and then fully in the calculator. Okay, give me just 1 second. I'm just going to take a drink here. Okay. So the first thing we need to do is we need to calculate our T alpha halves. We're going to plug it in to the E formula and then subtract the E from our sample statistic. Okay, so T alpha halves. We need to find that. We're going to do it by hand. So the first thing we need to do is find our degrees of freedom. Okay, degrees of freedom, DF, is your sample size minus 1. Okay, so we're going to do our degrees of freedom equals N minus 1. Our N is 16. So that's going to be 15. So our degrees of freedom is 15. Okay, so so we're going to go into the chart, which I'll pull up in a second here, and find where our confidence level, which for us is 95%, where 95% intersects with this degree of freedom, okay? And that's going to be our T alpha halves. If we don't have this exact degree of freedom in the table, we need to find the closest value we can that's less than it. Never go up, always go down if it doesn't have the exact degrees of freedom that you need, okay? All right, so in the book, this is just 2 pages over from the other table we were looking at, right? A18. So, pull up the book here, and we're going to go to A18. So this is a little different, right? T alpha halves, T scores, T distributions are a little bit different than Z scores, than your standard normal distributions. So you can see the way that it's showing up here is it's showing you, hey, there's a lot of different ways you can talk about this, right? If I have a, sorry, what were we? We are, in this problem, we're 95% confidence level. So it's saying, hey, you can think of this a bunch of ways. Either you can say, oh, my confidence level is 95%. But hey, that means that you have, in each of those individual tails, you have 2.5%. Or both of those tails together, your alpha, that's 5%. So whichever way you're thinking about it, I suggest just saying my level of confidence. Why do more math than you need to? And that's coming from somebody who actually enjoys math. But so just look at your level of confidence, and then you'll see over here is your degrees of freedom. So our degrees of freedom was 15, because degrees of freedom is 1 less than your sample size. So we're going to look up a degrees of freedom of 15 and a confidence level of 95%, 0.95. So degrees of freedom of 15, confidence level of 0.95, that gives me a T alpha halves of 2.131. Okay, 2.131. So T alpha halves is 2.131. Okay, or we could do that in the calculator. Okay, so how do we do that in the calculator? To find our T alpha halves, we just did it by hand, or in the calculator, very similar to this, except instead of inverse norm, we do inverse T. Okay, it's located in the same menu, second vars, right? Second vars, but it's number 4 instead of number 3. When you do this, though, the area that you give it has to be the area in one tail. Okay, now previously, when we were doing the inverse norm, when you're doing your z-scores, the calculator lets you do like, oh, is this the area to the left, the area to the right, the area in the center, the t-score? It doesn't let you do that. You have to give it the area in just one tail. So you have to find alpha halves. Okay, even if you're using the calculator, if you're doing a t-score, you have to find alpha halves because that's the area that you have to give it. Okay, so let's go ahead and find our alpha halves. So we go alpha halves is 1 minus my confidence level divided by 2. And don't feel like you have to like memorize this formula. Just think about visually what's happening. If I have 95% here, then that means both of these together are 1 minus 95%, or 5%. So if both of those together are 5%, then each one of these individually is 2.5%, which is what our alpha halves is, right? I wrote that super tiny. Can you guys even see that? I don't know why I wrote that so small. I got plenty of room on this page. I could write bigger. Our alpha halves is 0.025. So don't feel, like I said, don't feel like you have to memorize this formula. Just remember what's going on, right? 0.05 divided by 2 is 0.025. So alpha halves is 0.025. So we're going to go second vars DISTR, and then instead of 3, we're going to go 4 inverse T, right? Second vars, number 4 inverse T. the area that you give it has to be the area to the left, right? Area equals alpha halves, which is 0.025 or 2.5%. Degrees of freedom equals n minus 1, which is 16 minus 1, which is 15, right? So for the t-score, for the t alpha halves, you still have to do a little bit of work, even if you're finding it in the calculator, okay? So the area is 0.025. My degrees of freedom are 15. And there is my z-score. Or I'm sorry, not my z-score, my t-score, right? So if I'm doing it in the calculator, I can do it that way. It's much faster to do it on the table if you've got your table right there, okay? So one of the things that you learn as you're going through and doing the homework and doing the review assignments is you're getting a feel for when do I want to use the calculator and when do I want to just do it by hand, right? When's it going to be easier for me to do one of these things than the other? If they just want you to give them the confidence interval, you're just plugging it into the calculator, right? It saves you so much time. But like if all they wanted was the T alpha halves, then this would actually be faster to do by hand, right? Just looking it up in the table is faster. But all right, so either way, we've done that. We're doing it by hand. We found the T alpha halves. We're going to plug those into the E formula, our margin of error formula, and then we're going to add and subtract the error from the sample statistic. So again, what's our margin of error for when we don't know our population standard deviation? It's our T alpha halves, which we just found, times the sample standard deviation over square root of the sample size. Okay, so margin of error equals T alpha halves times S over square root of n. Okay, 2.131 times sample standard deviation is 31, square root of n is 16. That's just 4, but if you don't recognize that, that's fine. You can just plug in square root 16. You don't have to try and simplify things before you plug them in. Don't feel like you have to do that. Okay, 2.131 times 31 over square root of 16, or I could have just put 4. Okay, so we're getting a margin of error of 16.515. Okay. And we're going to take this and we're going to subtract it from the mean. And we're going to add it to the sample mean. All right, 645, and then take away my margin of error. 645 and add my margin of error. Okay, 645 minus 16.515. If I round to 1 decimal place, right, these answers are rounded to 1 decimal place, I get 628.5. And if I round to 1 decimal place, I get 661.5. So if we were to quote unquote interpret this, we would say we can say with 95% confidence that the true population mean falls in this interval, or falls between these numbers. Okay. So now let's do that fully on the calculator. Okay. So doing it this way was fully by hand. Finding your T alpha halves in the calculator and then plugging it in was partial calculator, partial by hand. Now let's do it fully in the calculator. So again, we can always refer back to our little sheet here. I want to find my confidence interval. I don't know my population standard deviation. So instead of doing a Z interval, I'm going to do a T interval. So again, it's in the same menu, it's in stat tests, but it's a T interval instead of a Z interval. Okay. So I'm going to go to stat, tests. Number 8, T interval. All right, see down here, just under Z interval is T interval. Again, you want to make sure that you're doing stats, not data. If it's on data, make sure that you arrow over to stats and hit enter so that you're plugging in stats, not data. And we're going to give it everything it asks for. It wants the sample mean. It wants the sample standard deviation. Don't forget, the S sub X is really just sample standard deviation, right? It wants the sample size. It wants the confidence level. So sample mean was 645, sample standard deviation was 31, sample size was 16. Remember, it was okay that it was less than 30 because it was normally distributed, right? And our confidence level is 95%. Okay, so let's plug it in. And there we have it. And again, if we round to 1 decimal point, we're still getting the exact same thing, right? 628.5, 661.5. This, much less work than all this. Again, it's important that you know how to do this, but when you're doing it on the test, this is all you really have to do. Okay, so just to confirm, it's always the positive T alpha halves that we plug into the margin of error. Yes, it is. Now, let's say that you forget that, right? And you accidentally plug in the negative. What's going to happen is you're going to get a negative number here. Now, hopefully, you'll recognize that and you'll say, oh, I just need to make that positive. But if you don't, there's a couple things you can do. You can switch it and say, oh, well, instead of subtracting a negative, which if you remember, sorry, is there? Oh, that's on my screen. I was like, does that look like it's a plus sign? No, it's not. I've just got schmutz on my screen. So if you were to subtract a negative, that would be like adding a positive. Well, if you're adding it, then it goes over on this side. And if you were to add a negative, that would be like subtracting it. Well, if you're subtracting it, it goes on that side. So the number that you get on the left side is always going to be the smaller number. The number that you get on the right side is always going to be the bigger number, because you're always saying that the mean is somewhere between here and here, a smaller number and a bigger number. Yep. All right. Okay. 10. Construct a 90% confidence interval for the population mean. Assume the population has a normal distribution. Thank goodness. In a recent study of 22 eighth graders, that's our N, 22. The mean number of hours per week that they watched television, sample mean, was 19.6 with a standard deviation of 5.8. That sample had that standard deviation. So that's a sample standard deviation of 5.8. Okay. And they want us to be 90% confident. So I've got a confidence level of 0.90 or 0.9. So I'm not going to do this one by hand because we're already at 4:33. And I want to make sure that we go through all the different types of problems here. So I did do one by hand. You guys know what that looks like. You can rewatch that problem. Let's just do this one in the calculator. So again, if we feel like we need to look back at this, we can, and we can remind ourselves that when our population standard deviation is unknown, that means we're going to use a t-test, a t-interval, okay? If you were doing it by hand, we're here in this middle column because we don't know our population standard deviation, so we're going to have to use a t alpha halves. We would plug that into the error formula and then add or subtract it. When you're finding your t alpha halves, when you're finding that, you need to find your degrees of freedom, and then you need to look at the table to see where your degrees of freedom and where your confidence level intersect, or you can find your degrees of freedom and then also find the area in one tail, right? Find your alpha halves and then do second vars to get it in the calculator, okay? We're not going to do all that. We're just going to do it in the calculator, okay? So we're going to go to stat, tests, number 8. I can either arrow down or I can just hit the number 8. and we're going to plug in what we're supposed to have. Our X bar, which is our sample mean, 19.6. Our sample standard deviation, 5.8. Our sample size, 22. Our confidence level, 0.9. Boom, there it is. And they're asking us to go to 2 decimal places because that's what all the answers are, 2 decimals. So there it is, 17.47, 21.73 when we round. Okay. T interval, because we don't know our population standard deviation, right? We don't have that. What we do have is our sample standard deviation. Okay. Construct a 99% confidence interval. For the population mean, assume the population has a normal distribution. That's good. A group of 19. Again, it's okay that it's 19. It's okay that it's less than 30 because it's normally distributed. A group of 19 randomly selected employees has a sample mean age of 22.4 years. The sample has that mean, and that sample has a standard deviation of 3.8 years. Round to the nearest 10th. Oh, did the last one actually specify? No, it didn't specify how many to round to, but this is specifying to round to the nearest 10th. So again, I could do this by hand or I could do it in the calculator. I'm just going to do it in the calculator. I have a sample standard deviation, not a population standard deviation. So I'm going to use a T interval. I'm going to go stat, I'm going to arrow over to tests, and I'm going to go down to 8, T interval. I'm going to plug in the stats that I was given. I was given 22.4 as a sample mean, 3.8 as sample standard deviation, sample size of 19, and a confidence level way up there at 99%. So if I round to 1 decimal place, that's what I'm getting. Right? Okay. All right, a random sample of 40 college students has a mean earnings of 3120 over the summer months. Assume the population standard deviation of earnings over the summer months for college students is, sorry, they said population standard deviation. Okay, population standard deviation is 677, and that the distribution of earnings over the summer months for college students is normally distributed. I mean, that's fine. It didn't have to be normally distributed because my n was greater than or equal to 30, but that's nice that it's both greater than or equal to 30 and normally distributed. Determine whether a normal distribution or a t distribution should be used. If I'm doing a normal distribution, I'm doing a z alpha halves. If I'm doing a t distribution, I'm doing a t alpha halves. Determine which one of those should be used or whether neither of these can be used. So again, we're going back to our requirements, right? Well, I mean, for anything, this is not a proportion problem. So we're not doing this one. We're looking at means here. So we're saying, does it fit this criteria or neither criteria? So the population standard deviation is known. It's a simple random sample, and it's either normally distributed or n is greater than or equal to 30. So check, check, check. And to be fair, actually, both criteria here are met. I really only needed one of these, but it actually had both of these. So absolutely, we can do a normal distribution, right? Our standard normal distribution, which is where we get our z-scores. A t distribution is where we get our t-scores. Right? Okay. So that's why we can use a normal distribution, because the normal distribution is our z-scores. I guess they don't really talk too much about, I mean, they kind of do a little bit of an intro into t-distributions, but t-distributions are a little bit different than standard normal distributions. And that's why we use t-scores instead of z-scores for them. Okay. All right, a random sample of 15 statistics textbooks has a mean price of 105 with a standard deviation of 30.25. Okay, so it was the sample that had that standard deviation, so it's a sample standard deviation. Okay. Determine whether a normal or a t distribution should be used or whether neither can be used. Assume the distribution of statistics textbook prices is not normally distributed. Okay, so let's go back to our requirements. I have a sample standard deviation as opposed to a population one. So I'm looking in this column, right? So population standard deviation is unknown. Yep, that's what's happening here. It's a simple random sample. Yeah, it sure is. And then I need to either be normally distributed. No, I'm not normally sorry. No, I'm not normally distributed. Okay, that's all right. As long as I have a sample size of 30, you guys can't see that. It's okay as long as I have a sample size of 30 or greater. But I don't. I only have a sample size of 15. So this is a check, but this is not. I needed to have one or the other of these, and I have neither of them. So it does not meet the requirements. So I can't use either. I can't use the normal and I can't use the t. Can't use the normal because I don't know my population standard deviation. And I can't use the remember z, t. I can't use the normal one, a z-score, because I don't know my population standard deviation. And I can't use a t distribution because I'm not either normally distributed or n is greater than or equal to 30. I mean, I'll take both if they're given them. They're not even giving me one, and I'm supposed to have at least one. It'd be nice if we had two, but you can have one or the other. So no, we cannot use the normal or the t-distribution. So you just like wouldn't be able to do this problem in this class. You'd be like, nope, can't do it. Don't have the tools. Okay, construct the indicated confidence interval for the population mean using the t-distribution. They just came right out and told you, hey, don't forget, you're going to use a t-distribution here because you have a sample standard deviation as opposed to a population standard deviation. Assume the population is normally distributed. So they're saying, hey, don't worry, it's okay, you're allowed to. So again, we're just going to use the calculator. This is a t distribution, so we're going to use t interval. We're going to stat tests number 8 t interval and plug in what we have. They've provided us the sample mean, the sample standard deviation, the sample size, and the confidence level. We want to be 98% confident. And then we're going to round to 1 decimal. And if you take those numbers and you round them to 1 decimal, you get the number sitting there. Okay. Again, if you were to do this by hand, you're going to, we're not going to do it, but you would find your T alpha halves, which it's faster to do it in the table. Find your degrees of freedom and then look up where your degrees of freedom intersect with your confidence level. Or if you were to do that by hand, you would need to calculate the area in one tail and then use second var's inverse t to get that t-score. So you're going to get the t-score. You're going to plug it into your E formula, which is here, along with your S and your N. And then you're going to add and subtract your E from your sample mean, your margin of error from your sample mean. Okay, that's what you would do if you did it by hand. We just did it in the calculator. It took me longer to explain how to do it by hand than it took me to actually do it in the calculator, right? Okay, in a random sample, 22 people. I'm going to label stuff up here. N is 22. The mean commute time to work was 34.5 minutes. And the standard deviation of that sample, so it's a sample standard deviation, was 7.1 minutes. Assume the population is normally distributed. Okay, that's good. And use a t distribution. They're telling you, hey, don't forget, you're going to use t distribution to construct what? A 95% confidence level or confidence interval for the population mean. And then they want you to find what is the margin of error. So we're going to talk about 2 different ways to find the margin of error. So let's just do this by hand first, or I mean, not by hand, sorry, in the calculator first. So same thing we've been doing for the last few, right? We're going to go stat tests number 8. This is a t interval, right? We're going to plug in what we have here, our x bar, right? Our sample mean 34.5, s, which is our sample standard deviation 7.1, sample size 22, which they told us it was normally distributed, which is why it's okay that we have a sample size less than 30, and we have a confidence level of 0.95. Okay, so we've got our interval here, right? Hold on. Sorry, I'm going to get a drink real quick. Okay, so I've got my, if I take these and round them to 1 decimal, I get these numbers. Okay, then they want the margin of error. Now there's 2 ways that you can do this. You can either go back and you can say, okay, well, in order to find my margin of error, I need my T alpha halves and I need my sample standard deviation and this. Okay, T alpha halves. Okay, I need to go find my T alpha halves. So I'm gonna, it's faster to do it by looking it up in the table. So I need my degrees of freedom and then I'm gonna look it up in the table where they intersect. Okay, then I get it and I'm gonna plug it in. You could do that. You could absolutely do that. Or you could say, what does this represent again? This represents my sample mean minus my margin of error and my sample mean plus my margin of error. So for instance, 31.4, that equals, this equals my sample. Sorry, I just hit the phone. I've got the phone at a weird angle here so that it can get out of my way so I have actual like table space. So it's like at a 45-degree angle and I just hit it and started a call. Anyway, this number right here is my sample mean minus my margin of error. 31.4 is my sample mean minus my margin of error. Well, if I want to find my margin of error, I have 31.4 equals, I know what my sample mean is. They gave that to me. It's 34.5. Now, I'm not going to do it this way because I don't want to go through an algebra lesson about dividing by negatives. So I'm going to focus on this one. 37.6 is my sample mean plus my margin of error. 37.6 is my sample mean, which is 34.5, minus, no, sorry, plus. The whole point was we're going to do the plus, the margin of error. Now we do need to do a little bit of algebra here, right? Hopefully your algebra skills are not completely dead. If I want to solve for E, I need to get this to the other side. This is a positive number, so to move it, I'm going to subtract. So in my calculator, I'm going to do 37.6 minus 34.5. That's 3.1. So my margin of error is 3.1. Now, if you don't want to think about it like this, if you don't want to actually like do like an equation, then just remember that whatever is here is you took the 34.5 and you added something to get to it. So the difference between them is your margin of error. Right? Your margin of error is what separates your sample mean from this number. Whether you're adding it or subtracting it, your margin of error is what separates your sample mean from this number. Okay, so if instead of doing an equation, you want to just like plug it into your calculator, you can. It would just look like this. You could do 31.4. To be honest, you could subtract 34.5 and you would just get a negative, because it's like, okay, well, I went to the left that many units, negative 3.1. And you would just need to make sure that you made it positive 3.1. But if that's confusing for you, if you're like, I don't know when I'm supposed to be using positive numbers and negative numbers, then just set up the actual formula or equation. Just say this number is equal to my sample mean plus my error, margin of error, right? Or like I said, you could go back and you could actually find your T alpha halves and then plug it into your margin of error formula and calculate it that way. But it's going to be, even though this is like not necessarily fresh in your mind, this is going to be easier than going back and doing the formula from scratch. And then of course they want us to interpret the results, which is what we've been doing this whole time. We can say with 95% confidence that the population mean commute time is between the boundaries of the confidence interval. A lot of times they'll actually go ahead and say, we can say with 95% confidence that the population mean commute time is between 31.4 and 37.6 minutes. Right? All right. Number 16, use the standard normal distribution or the t-distribution to construct a 95% confidence interval for the population mean. Justify your decision. If neither can be used, explain why and explain your results. Okay, this one's small. I'm going to zoom in a little bit more here. I know it's kind of blurry, but hopefully you guys can still see that. Okay, in a random sample of 11, so n equals 11, mortgage institutions, the mean interest rate, X bar, was 3.52%. Let's go ahead and leave everything as percentage rather than trying to take these and turn them into decimals, okay? 3.52%, and the standard deviation of that sample, so S, was 0.41%. Assume the interest rates are normally distributed. Thank goodness, because my N was only 11. And if they weren't normally distributed, then we wouldn't be able to do this because N has to be greater than or equal to 30. Okay, so first thing is they're saying, well, which distribution should you use? Well, we know, because we've done it a million times, that if I have a sample standard deviation instead of a population standard deviation, I know I'm going to have to use a T alpha halves, a T distribution, when I go to calculate all this, okay? So we need to use a T distribution because it's going through the checklist here, right? Population standard deviation is unknown. Well, it did it kind of out of order. It's a simple random sample. Population standard deviation is unknown, and the interest rates are normally distributed, right? They're normally just, can't see that. They're normally distributed. Even though n isn't greater than or equal to 30, that's okay. We just need one or the other of these. Okay. Then they want us to actually find it. Okay, so we know we're using a t-distribution, so we know we're using a t-interval. So let's go ahead and use that t-interval by going to stat, tests, number 8, t-interval, and plugging in the appropriate data, or not data, the appropriate stats, sample statistics. Eight, 9, 5. Okay, so if we go to 2 decimal places, right, they told us to go to 2 decimal places, we get these numbers. And then they want us to interpret the results again, like we've been doing. We can say with 90% confidence that the true population mean falls in the bounds of the interval, right? It's the whole basis of confidence intervals. Okay. All right, so now we're getting into proportions. Okay, so quick reminder, proportions. A few things about it. P hat is your X over your N. We're going to do some by hand. We're going to do some in the calculator. I need to make sure that N times P hat is greater than or equal to 5 and N times Q hat is greater than or equal to 5. Okay, a survey of 100 fatal accidents, that's N is 100, showed that 32 were alcohol related. That 32 is an X. Notice I did not put a bar over it, not an X bar, but an X. That's the number of successes, right? Remember your P hat is your X over your N, the number of successes over your total number of, your sample size. So we can find P hat because we have X and we have N, right? X is 32, N is 100, so P hat is 0.32. Okay, so just make sure that you don't accidentally call that an X bar. That's an X. Find a point estimate for P, the population proportion of accidents that were alcohol related. Okay, so let's go back. Let's remind ourselves what we're doing here. They want us to find, oh, I'm sorry. They're just, I was going to do way more with this problem. They're not asking us to find a confidence interval. They just want us to find the best point estimate. So remember when we did that problem earlier where it was saying the best estimate Oh, Alexis, yeah, I see your note now. Okay. All right, sounds good. Where earlier it was talking about the best estimate for the population mean is your sample mean, right? Well, same thing here, right? The point estimate for P is P hat. So we just found P hat. It's 0.32. Okay. Right. So same process here, a survey of 2,090 golfers showed that 302 of them are left-handed. Find a point estimate for the population proportion that are left-handed. So again, P hat is going to be your best point estimate for P, and it's X over N. X is the number of successes. Successes is not always a positive thing, right? Like in this last one, a success was a fatal accident that was alcohol related, as opposed to a fatal accident that was not alcohol related, right? So it's not always a positive thing, but remember when we're talking about proportions, it's successes versus failures, and they can call anything a success and the other one is a failure. So we're going to do X over N. So we have 302 over 2090, and we just plug that in. And then we round to the number of decimals that they have. Okay. All right, a researcher at a major hospital wishes to estimate the proportion of the adult population of the United States that has high blood pressure. How large a sample is needed? So we're going to be doing our N formula, right? Our N, finding sample size, right? Is needed in order to be, let's write some of this stuff down, 98% confident that the sample proportion, also they're flat out telling us this is a sample proportion, will not differ from the true proportion by more than 2%. So our margin of error is, and be careful here, you have to write your margin of error in decimal form. Let me listen. All right. So just to recap that, you have to put your margin of error in decimal form. Okay. So we go back to our formulas and we have when p hat is known and when p hat is unknown. So did they give us a p hat here? No, they didn't. They didn't even give us an x over an n or an x and an n in order to find our p hat. So that's okay because if p hat is unknown, we can just assume that it's 0.5. Okay, so let's go ahead and write some stuff out. P hat is going to be 0.5. So if p hat is 0.5, q hat is also going to be 0.5, right? Because q hat is the complement of p hat. Okay. All right, now we need to find, the formula calls for a z alpha halves. So remember, your z alpha halves is dependent on your confidence level. Again, you can do it by hand where you're saying, okay, this is 0.98. So both of these together are the other 2%. So each of these individually is 1%. And I'm going to go look up in my table. If I have an area of 1%, what's the corresponding z-score to that? Or I could look up in my table 98% confidence level. Let me go to the right page here. But we look at our table and it doesn't have 98%. So we could look it up here, but I'm just going to do it in the calculator because I think that's going to be faster. So again, how do we look that up in the calculator? If I want to find my z alpha halves in the calculator, I'm going to do second vars and I'm going to give it my confidence level in the center. Right. So I'm going to go second vars, inverse norm because this is a z-score. The the area is my confidence level, and I can give it that as long as I tell it that that's the area in the center. Okay, so I'm going to take the positive, so that gives me a z alpha halves. I'm going to take the positive one of 2.3, I'm going to go to 3 decimals, 2.326. All right, so now that I have that, now I'm going to plug it into my formula, right? So here's my formula. I'm going to copy it down on the paper. Okay, so we have n equals p hat times q hat times z alpha halves over our margin of error squared. Okay. Now, what you're going to find is if you're not given your p hat and your q hat, they're going to be 0.5, which is going to make this 0.5 times 0.5, which you can just do that in your calculator. Like you can plug everything in, or you might, I mean, if you do this enough, you're going to end up remembering that, okay, half of a half is a quarter. So this turns into 0.25. So you might see some formulas where they actually give you a different formula here, where instead of saying p hat, q hat, and tell you to assume it's 0.5, they'll actually just put the number 0.25 here. So just be aware that that's not like, oh, it's a different formula. It's the same formula. They're just saying this is what you would get if you make that assumption. Okay. All right, hang on just one second. I'll be right back. I'm good here. I know. We're good. Yeah, I'm gonna look. Drive safe. All right, so let's go ahead and plug everything in. So we've got 0.5 times 0.5. We've got our z alpha halves, which we found to be 2.326. We've got our margin of error is going to be 0.02, and we're going to square that. Okay. All right. Now remember, this is n, this is sample size. So that means that whatever number we get, we need to make sure, excuse me, that that we go up to the next whole number. Okay, so I'm going to do 0.5 times 0.5 times 2.326 over 0.02, and I'm going to square that. Okay, and okay, so I'm getting a slightly different number here, and I don't like that. We don't like slightly different numbers. We need to get the same number. So let me check something here. Okay. All right, you know what I'm going to do? Instead of using the number from the calculator, I'm going to use the number from the table. Let's see how much of a different number we get, which, by the way, as an example, if you're doing, oh, also, I just real quick, I tested here. I was like, was I not supposed to make that a decimal? I absolutely was. So we're ignoring that. So what we got was 3381 point blah, blah, blah. So let me write that down because that is what we got when we plugged this in. We got 3381.4225. We take that, we need to say that has to go up to the next whole number. So 3382. Okay. Now, if you did this, what number is the closest to that? Well, it's going to be this one, okay? Now, I don't like how far away that is, so I'm going to take a second and we're going to say, well, what if I used the table in the back of the book to get the z-score, okay? So this is a 98% confidence interval. We did this over here, right? So the area to the left, the area in one tail is 0.01. So I'm going to look up an area of 0.01 on the table here. All right. And we're going to say, okay, so 0.01, actually, it's funny because we had similar, right? So like this is 2 away from 100. This is 1 away from 100. So we're going to use this. So this gives me 2.33. Okay, so I'm going to use a z-score of 2.33 rather than going that many decimals, okay? 0.5 times 0.5. 2.33, which, I mean, if you see here, if you rounded that to 2 decimals, you'd get 2.33, right? 0.02 squared. All right, so let's see how much closer we are here. You don't have to have that times. If you have a number sitting next to a set of parentheses, then you know that it's, or the calculator knows that you are, yeah, there we go. 3393.0625. And then that goes the next whole number up to 94. And that's how they're getting that number. Okay. So if you have a fill in the blank, then feel free to, use several decimals, excuse me, throughout what you're doing and just round at the end. I think we talked about that a little bit earlier. Like, hey, is it okay to like round to this or that? Or for a lot of things, you want to wait to round until the very end. But when it comes to these z-scores, if you're looking something up in the table, it's okay to just use the 2 decimals that it gives you in the table. Okay. For this, they calculated it using just the 2 decimals that you get in the table. Okay. But again, if you did it this way and you got this number, use your critical thinking skills and say, okay, that's the closest one. But then also, if you have time, go back and check and say, okay, well, if I look it up in the table, will I get exactly that number? And then you'll feel better. Okay. All right, a researcher wishes to estimate the number of households with 2 cars. How large a sample size, again, we're going to be looking for an N, is needed in order to be, start labeling things, confidence level of 98%, that the sample proportion will not differ, also proportion, will not differ from the true proportion by more than 4%, so our margin of error is 4%. Okay, a previous study indicates that the proportion of households with 2 cars is 19%, right? So let's see, where was that written? I thought I had something there. Oh no, I was thinking of where it talks about like a preliminary random sample had to have n is greater than 30. Yeah, this is a proportion, so we're using this, okay? So a previous study, that means that we have a previous p hat. So p hat is 0.19. So if I have p hat, I can calculate q hat because it's 1 minus p hat. So that's 1 minus 0.19, which is going to be 0.81, right? 1981, yeah. All right, so let's find our z alpha halves, which is based on our confidence level, right? We're going to check the table in the book to see if it has a 0.98. If it doesn't, we're going to remind ourselves that if I have a confidence level of 0.98, that means the area in both of the tails together is 2%, which means that the area in one tail is 1%, and we're going to get the z-score that separates the area of 1% from the rest. So we're going to go to the back of the book, and this was actually the same number that we did before, right? We didn't have 98% here, so we have to say 1%. We find 0.0099 is as close to 0.001 as we can get, and that corresponds to 2.33. Technically, it's negative 2.33, but we're going to be taking the positive of that because we always use the positive when we're doing our z alpha halves or t alpha halves. Well, really, only if you do the z alpha halves might you get a negative 2.33. Okay, so we found that, and now we're going to use the formula. We're going to rewrite the formula. I'm just kidding. So, right, we've got our sheet here. We're going to rewrite that formula. We're going to do that formula. So n is equal to p hat times q hat times z alpha halves over our margin of error squared. Okay, p hat is, I'm going to put these in parentheses just because when I got a lot of decimals going on, sometimes the decimals and the multiplication symbols can get mixed up. Our z alpha halves was 2.33. Our margin of error was 0.04. And we're squaring that. Okay. I'm And then don't forget your squared button is that, you can't see that, is this little button right here, x to the second power, or you could hit the caret symbol and then say 2, but it's faster to just hit the squared button. Okay. All right, so when we do that, we get this number, get about 522.1923188. And again, if I only include 522 people, it's not enough. I haven't hit the threshold that's required to be this level of confident with only this margin of error. If I need to have this many people, I'm not cutting people into pieces. I need to go up to the next whole number to say 523 people. And that's how they're getting 523. Okay, let P be the population proportion for the following condition. Find the point estimate for P and Q. Okay, a study of 4237, so N is 4,237 adults from country A. Oh, okay, from country A. They're just labeling it as country A. In a study of this many think that mainstream media is more interested in making money than in telling the truth. I'm not allowed to comment on these things. Okay, so this right here is an X value, right? That's how many people. Our P hat is our X over our N, right? 2486 over 4237. And we plug it in. Okay, so when we do that, we're getting 0.58, and if we round to 3 decimals, 587. Okay, so that's P hat. So remember, Q hat is the complement of that. It's 1 minus P hat. Now, if you wanted to, you could do it as a fraction. I'm going to do it as a decimal first because that's going to be the fastest way, because I'm just going to subtract this decimal, right? I'm just going to say 1 minus 0.587, or I could have done, when I was here at 2486 divided by 4237, I could have done 1 minus and then second answer. Down at the bottom of the calculator here is the answer, so you can do second answer, so second and then this button, and it says, oh, you want me to take the answer that I had and subtract it from 1, and you get that. But I didn't want to have to take that and round again, so I just plugged that in, 1 minus 0.587, and I'm getting 0.413. Okay, if you were being required to represent it as a fraction instead of a decimal, then you would say, okay, this is my sample size. Well, if this many people do think that, then the rest of them don't think that, right? You're either P or you're Q. It's one or the other. You either do think it or you don't think it. That's how these surveys work. So binomial, right? So I could just subtract this from this, right? I've got like the whole group here is 4,237. This is a little bit more than half. I don't know about that, is 2,486. So the rest of them would just be 4237 minus 2486, right? 4237 minus 2486. So, 1751. So there's 1751 people who don't think that, right? So if they wanted it as a fraction, you would have that your Q hat is 1751 out of 4237. They're not asking for that, but if they were asking for it in that format, that's what we would do. Okay. All right. Okay, we're almost done. Got just a few more left. In a survey of, that's N equals 2266 adults, 705, that's an X value, 705, say they believe in UFOs. I believe. Right? Isn't that Mulder and Scully, right? Mulder was, I believe. Okay, X over N. They gave me an X, they gave me an N. I could find my p hat. 705 over 2266. Let's plug that into the calculator. I'm just plugging stuff in before we even finish the problem. So my p hat is about 0.311. Okay, so let's see what they're actually asking us to do. They want us to construct a 99% confidence interval for the population proportion of adults who believe in UFOs. So let's go back to, if we were to do this by hand, I don't think we've done one of these yet by hand. So we're going to do this one by hand, and then we're going to do it in the calculator. Okay, hold on just one second. Okay, can you still hear me okay? And to switch up my
Yes, I can hear you.
Okay, good. All right, so we're going to do this by hand, and then we're going to do it just in the calculator. So how do we do it by hand? We calculate our z alpha halves. We plug the appropriate values into our error formula. We add and subtract our error from our sample statistic to create the interval. Okay, so for proportion, we're going to get a z alpha halves. So how do we find our z? If our confidence level isn't shown in the table, we have to do that. So what's our confidence level? They want a confidence level of 99%. Let's look at the table. The table gave us a confidence level of 99%. The corresponding z-score, the critical value, is 2.575. So I'm going to do this. Yeah, let's do this over here. My z alpha halves is, what was that again? 2.575. Okay, found my z alpha halves by looking at the table. If it didn't have it, I would have to do the whole, here, I'll do it up here. I would say, okay, this is 99%, which means 1 minus 99% is 1%. So what's in each of these is half of a percent, or 0.005. So I need to look up in the table the area of 0.005 and find the corresponding z-score to that area. And that's going to give me 2.575. Actually, it's going to give me negative 2.575, but then I just make it negative. Or I mean, I make it positive. Okay, so I have my z-score. Now I'm going to plug the formula, plug the numbers into my error formula. Okay, so we're going to write that down. My error formula is z alpha halves times, and then we've got the square root of p hat times q hat over the square root of n. Okay, well, we don't have q hat yet. We have p hat, but we don't have q hat. So let's go ahead and calculate q hat. Q hat is 1 minus p hat. So it's 1 minus 0.311, which, let's just be sure. I'm not going to do that in my head just to make sure I don't make a mistake. All right, so I've got my p hat, I've got my q hat, I've got my n, and I've got my z alpha halves. I have everything I need to plug into my error, my margin of error formula. Right, calculated my z alpha halves. I'm going to plug everything into my margin of error formula. Then I'm going to add and subtract that from my sample proportion. Okay, so we have, here, actually, I'll do it under here. I'm going to run out of room. 2.575. P hat is 0.311. Q hat is 0.689. And N is 2266. Okay. When you're doing this, make sure that this number in the denominator stays underneath your root. right? You see how this line on top is continuing to extend? That's because this is underneath the root, okay? All right, so we're getting a margin of error of about 0.025, okay? So I'm going to take my sample proportion and I'm going to subtract my error. I was about to write mean. It's not mean, it's the population proportion. And I'm going to take my sample proportion and add my margin of error, right? Same process that we do with the mean, just with the proportions. So I have, okay, so I have my p hat, which is 0.311. I'm going to subtract 0.025. And I have my p hat, which is 0.311. And I'm going to add my margin of error, which is 0.025. Okay. Right, so I get 0.286 and I get 0.336. Okay, so I'm glad that the way that we did our rounding, we got exactly what they wanted us to get. So we can say, right, because they always want us to interpret, we can say with 99% confidence that the true population proportion lies in this interval, right? The true population proportion is somewhere between 0.286 and 0.336. Okay. All right. A researcher wishes to estimate with 99% confidence the population proportion of adults who support labeling legislation for genetically modified organisms. Her estimate must be accurate within 5% of the true proportion. Okay, so what it just gave us there was a confidence level. I'll write it off to the side here. Confidence level of 0.99, and it gave us a margin of error of 5%. Your margin of error needs to be in decimal form, right? If they give it to you in percentage form, you have to write it as decimal form. Always remember that. Okay, no preliminary estimate is available. Find the minimum sample size needed. Okay, so again, we're going to do the exact same thing we did before. Oh, shoot, I'm sorry, I forgot. I was going to show you how to do this fully in the calculator. Sorry, let's go back. Let's do this fully in the calculator. All right, how do we do that fully in the calculator? It's in the same menu as the other ones, right? Stat tests, but we're going to go all the way down to alpha, right? These were number 7 and number 8. This is all the way down in the letters. Alpha, it's 1 prop z int, right? A proportion, we're using z-scores, we're finding an interval, okay? And you're going to plug in your values. And remember that p hat is x over n. I forget off the top of my head if you have to plug in the x and the n or if you have to plug in the p hat. I think you plug in the x and the n. But all right, so we're going to do this in the calculator now. Right, we're going to go, so that was if we did it by hand. Now we're going to do in the calculator, we're going to go stat, tests, then we're going to go alpha, which is 1 prop z int. Okay, zoom out just a little bit here. Okay, so stat, test, and you can either arrow up to get to A, or if you're here, you can arrow down to get to A, or you can say, well, I just want to go directly to A. So you would say, okay, well, where is the A? It's the yellow above. It's kind of hard to see in this light, but it's the yellow above on my calculator. It's above the word math. So I'm going to hit alpha math, and that goes to the A option. Okay, so it wants my X, my N, and my confidence level. So if you're doing this in the calculator, you don't even have to calculate your p hat. You just need your X and your N, right? If they give you your p hat, like let's say they tell you that your p hat is 0.406 or something, you can just put 406. Well, actually, you know what? I'm not going to say that because they're not going to do that. They're going to give you your N. You're going to have your N. So that makes a difference. Anyway, okay, so our X value is 705. Our N value is 2266. And we want a 99% confidence interval. Okay, so there we have it. So if we take those numbers, we round them to 3 decimal points, that's what we're getting. And then it tells you, hey, by the way, I calculated your p-hat for you. So if you need to know your p-hat, you can also have it do it that way, but it's faster to just plug it in. So you can see the difference in this, right? So again, stat, tests, and then you go down to A, you have to tell it your X, and you have to tell it your N, and you have to tell it your confidence level, and you get your answer. Or you could do it this way, right? Okay, hopefully you guys get the getting the pattern by now, that when you're doing a full confidence interval, it's faster to just plug it into the calculator. Okay, now we're going to do this one. So yeah, for the purposes of time, let's just do a confidence interval. Hang on just 1 second. Okay. All right, so oh, I'm sorry. This is a different problem. They're not asking for a confidence interval. They're asking for the sample size, right? So we're doing we're doing this formula here because we're dealing with proportions, right? So they didn't give us, no preliminary estimate is available. We don't have a p-hat and a q-hat. Well, that's okay, because if p-hat's unknown, we can assume that it's 0.5, right? We can assume that they're 50-50. So we're going to say p-hat, we're going to assume is 0.5, q-hat, we're going to assume is 0.5. So let's go ahead and plug these in. We have n equals p-hat times q-hat times, we need to have our z alpha halves over our error, and we need to square it. We need our z alpha halves. Remember, the z alpha halves we get, it's based on your confidence level. So it's going to be a z-score. Let's see if our table shows us real quick what this is, so that we don't have to either put it in the calculator or look it up on the table, like say, oh, if there's the area and then what's the thing? It might be in that tiny little table. Because if it is on the tiny little table, it saves us time. And sure enough, there it is, 0.99. The corresponding z-score is 2.575. So awesome deal for us. 2.575. And that's even faster than getting it in the calculator. Okay, so we're going to do p-hat of 0.5, q-hat of 0.5, z alpha halves of 2.575, margin of error of 5%, 0.05, and we're going to square that. Make sure I type that in right. Okay, so we get 663.0625. Excuse me. And what do we do with these when we're finding sample size? We always go up to the next number, right? Oh, how did I get 64 when they got 666? All right, let me see if we only go to 2 decimals here. Let's see if that gets us the number that they're looking for. Let's see if that does it. Oops. So I'm going to say, hey, take this and copy it, make this number, if I only go to 2 decimals there, whoops, would that get me? Yeah. So if you take, I know we just got this from the table. I'm not sure if they would actually mark that wrong. You got that from the table. Let's see, did they specify that you have to take your z-score to 2 decimals? No,
I
they
remember,
didn't specify.
sorry, for I watched your other, I think it was the 8 week term or something like that. You
Mhm.
mentioned that the review homework, there was a mistake on one of them.
Okay. Yeah, so I do remember that, but I don't think it was this one because it was like a glaring mistake. Whereas this can be corrected by a rounding. But good memory. When we do that one in the 16 week, I'll be sure to point that out. But yeah, so I would say to from what I'm seeing on the homework, I would say go take your z-scores to 2 decimal places because that's what it appears to be going to. Now, if you forget that and you go and you just pull what it has in the table, because to be fair, the table itself, that tiny little table, is giving us a full 3 decimals. If you get an answer and it says that it's wrong, I would check with your instructor because they might be able to go in and change it. Or they might say, oh, no, the system is programmed to take both answers, right? So like it might say, oh, well, since we know this is a table or a number that's that's in the table in the back, we know that we can say 664 is an answer. Or if they take their z-score and they round it to 2 decimal places and they use 2.56, or sorry, not 7, 8, that rounds to 8. If they go to 2 decimal places there and they get 0.05, that's going to go to 665.64, which goes to 666. Okay, so you could get this or you could get this, and I would that might be specific to your instructor, where your instructor might say, yeah, I'm going to accept either one. The system might already be set up to take either one, or if you get one rather than the other, you might need to reach out to your instructor and say, can you please, like, here's my work. I got this from the table in the back. Can you either tell me what I did wrong, or can you please change it so that it tells me that that it gives me credit? Um, okay, and then for B, it says, what's the minimum sample size needed using a prior study that found that 74% of the respondents support labeling legislation? Okay, so now what they're saying is, okay, before we didn't have any prior studies. Then we do a little bit more research and we find that, oh, wait a minute, I do know a p hat. I have a p hat of 0.74. So my q hat is going to be 1 minus 0.74. So that's going to be 0.26. And so now when I go to plug this in to my sample size determination, not using 0.5 and 0.5, I'm using 0.74 and 0.26. And we're going to go ahead and use the same z-score that we had up here, right? Because everything else is staying the same. The only thing that we're changing here is our p hat and our q hat, right? So we have 0.74 times 0.26. Oh, I should have just done the copy and paste thing. That's okay. 2.58 divided by 0.05, and that's being squared. And we get 512.276544, which what do we do with that? We go up to the next whole number of 513. So if we take a look at this, we see if we have no prior information, well, we better get a whole bunch of people. But if we do have some prior information, we don't need quite as many people. It's more than 100 fewer people that we need here, right? Because we have more information, so we don't need as many people to be as sure, right? So having an estimate of the population proportion, it reduces the minimum sample size that's needed, right? The more information you have, the better, the less your sample size has to be. All right. I'm going to get a water. Give me just a second. Okay. A researcher wishes to estimate with 90% confidence population proportion of families who eat fast food at least once a week. Her estimate must be accurate within 2% of the population proportion. So again, we're going to write that down. It's a confidence level of 0.9 or 0.90. Our margin of error needs to be 0.022%. No preliminary estimate is available. find the minimum sample size needed. So since we don't have a p hat and a q hat, we're going to assume that they're both 0.5. We're going to find our z alpha halves. 90% confidence level. When we look to the table, thankfully, it does give us that 1.645. Now, I'm not going to use 1.645. I'm going to use 1.65 because I'm going to go to 2 decimal places because it seems to like the 2 decimal places. So I'm going to use 1.65. Also, if we were to look this up in the table, we'd get we'd get 1.645 because it would be halfway in between, but we're going to go to 2 decimals, 1.65. So my Z alpha halves is 1.65. Or you could find that in your calculator by plugging in 0.9 into your inverse norm and telling it that that's the center area. And if you go to 2 decimals, you're going to get 1.65. Okay, so we have our formula, which is, I'm going to start it way over here, running out of room. N is P hat times Q hat times Z alpha halves over error squared. So we have P hat is 0.5, Q hat is 0.5, Z alpha halves 1.65, margin of error 0.02, and we square it. Okay, so yeah, I don't like that at all. That's no good. It's way off from theirs. I don't think that this was the section that had the wrong number because that's just such a very wrong number. Did I plug? Oh, I sure did. Look what I did. My number is so different. This is 1,692 and I'm getting 17,000 because look what I did. I didn't plug in a 0.5, I plugged in a 5, right? So that's not like, oh, it's a rounding issue. I'm off by a huge magnitude. This is, I don't know if you guys remember me talking about it in previous reviews that, it's always a good idea to like check your answer, say, does it kind of make sense in the context of the problem? This is a great example of no, that doesn't make sense. Well, I mean, if I'm comparing it to the correct answer, like if you don't know what it's supposed to be, then you have no idea. But, if you're looking at comparing that, it's like, yeah, that's way too far off. That's not a few digits off. That's 16,000 off. So then I go back and I see, oh, right, because I didn't multiply it by 0.5, I multiplied it by 5. So let's try that again. Okay, so I am still not getting as close to this as I want. So even though I said I'm not going to use 1.645, let's go ahead and use 1.645. So and there it is. Okay, so it's being wishy-washy. Okay, so in one, when we used all 3 values that we were given in the table, it didn't, that's not the number it gave us. But for this one, we do need to use all 3 numbers that it gives us in the table. So what I think a fairly safe assumption would be is that it's going to accept either answer. Again, if you're feeling unsure about that, if you're like, I don't know, man, talk to your instructor. Say, look, what does it want me to do? Like, if I go to a whole bunch of decimals with my z-score, is it going to accept my answer or do I have to go to a certain number? Because in this instance, on one problem, it doesn't like it when you go to the 3 that it gives you, and in another problem, it makes you go to the 3 that it gives you. Okay. So if we do, just going to write this out, 1.645 over 0.02. That's going to give us 1691.2656, blah, 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 blah. And what do we do with that? We go up to the next whole number to get our 1692. Okay, so we got our 1692, and then it says, What if we uncovered that there was a prior study? Yay, more data, more information. That's always good, right? More information, the better. That found that 22% of the respondents eat fast food at least once per week. That is our new p hat. P hat is 0.22. Great. So we're going to do 1 minus that to get our Q hat. So that's going to be 0.78. Right? Right? Am I having a brain freeze? Yes. Okay. All right. So now we're going to do this again. Same formula, except, excuse me, instead of 0.5 and 0.5, now we have 0.22 is our P hat, 0.78 is our Q hat. We're going to do the whole 645 because that's what it liked. Okay. Okay, and we get 1160.884725. Whether this was an 8 or a 0, if I have anything after the decimal, I have to take this and I have to go up to the next whole number, right? I have to go up to 1161. Okay. All right. So again, it's asking us, hey, make an inference about that. Talk to us about what the heck just happened. What does this mean? Having an estimate of a population proportion, it reduces the minimum sample size needed, right? If we want to stick to that level of confidence and that margin of error. Okay, and oh, that was the last one. I don't know why I have a blank page. That was it. That's the end. All right. So that was a long one, but again, I am going to try and get this out to you guys tonight so that you can have the handout that has, you know, this information and the step-by-step and the formulas, right? And the reminder of what the heck confidence levels are graphically and all that. So yeah, thanks for sticking with it. I'm glad that you guys are getting, you know, a little extra help here. And don't hesitate, as always, to reach out, go to your ASC, reach out to your instructor, connect with somebody from the ASC on the chat. I'll have all the information about that in the email that I send out. So, all right, you guys have a fantastic night and good luck.
Thank you so much. Have a good night.
You too.